I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists.
Thank you for being here. Our speaker, Rana Adhikari, is professor of physics at the California Institute of Technology, Caltech, where he leads the Adhikari Research Group in experimental gravitational physics. Rana earned his bachelor's degree in physics at the University of Florida and his physics PhD at MIT. Rana's doctoral and postdoctoral work focused on the use of lasers to detect and analyze gravitational waves. Notably, Rana was research assistant to Rainer Weiss, co-recipient of the Nobel Prize in 2017 for development of LIGO, the Laser Interferometer Gravitational Wave Observatory. And now, the Adhikari Research Group has branched out to perform tests of fundamental physics in general, including tests of quantum mechanics as well as gravitation. However, I suspect that Dr. Adhikari's true scientific love has always, and still is, been lasers. In fact, one of his very popular YouTube videos is entitled, "Whatever it is, if you add lasers, it's better." Please join me in welcoming gravitational wave pioneer and laser lover, Dr. Rana Adhikari. Now, did I inadvertently mute him? Oh, no. No, he's there.
All right.
Here we go.
I think I know what I'm doing now. Let's see. Oh, no. All right. Yeah, as always, navigating slides in Zoom is one of the challenges of experimental physics these days. But I think I've got it. Anyway, thank you for that nice introduction. I should add a few things. I think when people think about physicists or astrophysicists, sometimes there's a little bit of a feeling you may be getting somebody who spends a lot of time at the chalkboard with equations. And I do my part of that, but maybe it'll give you a better flavor of things to say. Before I got to college and started doing physics, I was an auto mechanic in Central Florida on the East Coast, close to Cape Canaveral. And most of the time what I was doing after high school was fixing cars of NASA engineers who were working at the Space Center. And I think if nothing else, it imbued in me a sense that you don't have to be all that special to work on space. Things are going on in space with NASA because these were people who needed my help with an oil change. So my background is really on the experimental side of things. But I'll be talking both about the theory of cosmology and physics, as well as the details of the experiment. And so feel free to ask me things from either side. I'm not really a jack of all trades, but I know a little bit about all the trades. So here we go. So on this first page, you see this image, and what it's meant to imply, you see the dark spots there in the image, and those are black holes. And these sort of wavy grid lines that you see are meant to give some sort of feeling about how space and time together are warped by the presence of massive objects like black holes. And this happens not just with black holes, but with everyday objects. Everything warps space and time. And that concept is due to Einstein, and I'll get into it, mention bits about it as I go along. But anyway, that's what the graphic is meant to imply. It's an artist's conception of things. So we haven't actually seen anything like this, but we think this gives a good impression of what we're looking at. So, and I'll describe how these things work with it. So the experiment that I've spent, by the way, is my audio fine? You're able to hear me?
I think you're doing well. Thanks, Rana.
Okay. So the experiment that I've been working on for now a little bit over 20 years is LIGO, the Laser Interferometer Gravitational Wave Observatory, which is sort of a mouthful, which is why we have an acronym. And you may have seen things about it in the press. I was amazed by the reception that we got back in 2016. We had been toiling away in obscurity for decades, and for my advisor, Ray Wise, he had been thinking about these things for something like 50 years. And to wait that long is a true test of patience and perseverance, I think. I thought 5 years was a bit too long to wait. And then when it took me 20 years to see something, I was, yeah, anyway, it was a long haul, But I'll describe a little bit what the experiment is and how does it work. But at one level, you can think about it, the LIGO experiment, as a really massive, sort of kilometers large instrument, which is essentially a microphone, and it detects the vibrations of space and time, which means out in the universe, maybe billions of years ago, some sort of huge event happened, a cataclysmic event, like stars smashing into stars and explosions that are, zillions of times more bright than anything in the galaxy. And when those kinds of things happen far out in space, space itself rumbles. And what's it mean for space to rumble? The LIGO experiment is essentially like a microphone of space. And so the right way to think about it is when these events happen in space where there's things orbiting each other or things vibrating far out in space, and these are not anything on the Earth, nothing on the Earth is strong enough to do this. It has to be the most massive events, galaxies merging into galaxies and that sort of thing. And when it happens, there's actually a vibration in space, and you'll see a wave coming to us. And the effect of that wave it would appear to us as an actual stretching and squeezing of space. And so you would look out, and events that look like a certain size would actually move back and forth. And so it looked like the apparent size, for instance, of the whole Milky Way galaxy would sort of move back and forth like this. And so it's a sort of an apparent fluctuation that you see. And this type of thing, it's a little bit like a sound wave. When a sound wave comes to us through the Earth's atmosphere, you see a sort of a pressure wave building up in the air, and we hear it because our ears are sensitive to the fluctuations of the air, and that's sort of what sound is. And so LIGO is like that. It's a great microphone for space. And if you
please shut the fuck up.
If you look at this plot that you see, the colorful one, and you see on the y-axis, the vertical axis, there you're seeing the frequency of the signal, and on the x-axis or the horizontal axis is time. And it sort of looks like maybe this thing is a astrophysical signal, but actually that thing that I'm plotting is just the sound you get from birds. And I put that on there so you can get a sense of, in some of the later plots I'll show you, I want you to get a physical sense of what these plots are showing. And so when a bird makes a chirp, it's like chirp, 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 like this, and you see it's a kind of a broadband signal. It's in the human audio band. And the signals that we see from space, they're also in the human audio band, that they're the kinds of sounds that you're used to hearing, high frequency sounds, low frequency sounds, but it's sort of like birds and humming and buildings and that sort of thing. It's things that have the same kind of character that we detect are the same kinds of things that you hear all the time. And now you look at this added graphic that I put there. You see the same kind of shape. There's at the bottom, these sort of colorful images. These are the actual gravitational wave signals that we found in late 2015, and then what followed was a huge media splash, and people were able to hear about it when we made the announcement early in 2016. And what we are plotting there is the actual stretching of space that we detected with our instruments. And it's really, this was an amazing thing. And the reason we had all of this press coverage is it's a measurement that people thought impossible for many, many years. And Einstein himself, when he came up with the idea in 1918, said, well, it's nice. Here's a calculation I've made, but maybe this thing is going to be too small. It's not a thing that anyone's ever going to find. And to give you an idea of how small it is, in a physicist's lingo, we say it's a strain of 10 to the minus 21, which is a kind of an obscure way to say what's happening. But the way you should think about strain is similarly to what happens when the moon travels around the Earth. The moon pulls gravitationally on the near side of the Earth more than it does on the far side. And so the Earth itself is stretched by a certain amount, and we call that a strain, meaning it's been strained. And if you move the entire Earth, if you stretch it by this amount, 10 to the minus 21, that means that the actual size of the Earth has changed by about something like the size of a proton. So it's billions of times smaller than what anybody can actually see. So it's an incredibly small measurement, a small distance that we're measuring, and so it was really challenging to do. And to give you an idea of what this means, small things, nanometers, it's a lot of lingo thrown around, but you can look at some of these things. So on this picture, this is the big brown thing on the right, and that's about that's a human hair. And so the width of a human hair, if you have dark hair, it's about 1/10 of a millimeter. And progressively, all of these objects get smaller and smaller as a human hair, salt, cells, and then you get all the way down to the left-hand side, and you're at the size of viruses, which are still, any of those viruses are something like 1,000,000 billion times bigger than the size of the motion that we're trying to measure. So very, very challenging. If you have a hard time grasping the size, you're not alone. I found a lot of times it's really tough to get a intuitive grasp for what's going on, what's it really mean. But let's just say it's a tiny number. We're trying to measure something really small. And the reason for that is not that the space-time fluctuation is weak. It's incredibly strong, but it has to do with the fact that space and time are stiff. So, like I said at the beginning, I'm not a scientist on the chalkboard a lot. And so this is probably the only equation that I'm going to show here, which is the thing in the yellow that says G something something 8 pi, whatever. And what that equation is telling you is that on the left-hand side, that's the curvature of space. Is space normal like what we see, or is it curved, or is it bent a little bit? And on the right-hand side is all of the stuff that causes this curvature. And the thing to see on there is that there's this symbol c, which is the speed of light. And light moves really fast. It's the fastest thing anyone knows about. And it's to the 4th power. So you have to divide whatever kind of mass you have by the speed of light 4 times before you find the curvature. And so the way to think about it is that space itself is sort of like this mesh. There's grid lines where all the objects are on their coordinates. And when there's a space-time wave, it means that those objects, if you were to draw grid lines on them, or if you look at my shirt, which kind of looks like a grid line, when it fluctuates, you'd see this kind of action like what you're seeing on my shirt here. There's an actual stretching of space. And the way that we measure this is with a device that's called a laser interferometer. And that's pictured there in the bottom of the graphic. And let me just walk you through it. So there's a laser which sends out a light beam of some kind of color. In our case, it's infrared, but you can imagine it just to be red or blue like it's shown on there. So the light comes, it hits this thing called a beam splitter. And the beam splitter is it's a piece of glass. And some of the light goes through the beam splitter and some of it's reflected from the beam splitter. It then travels 2 paths. It goes down to the ends where there are mirrors that reflect, and then that light comes back together. And when it comes to the beam splitter, those 2 light beams merge, and then they go to the thing which is called a light detector. And normally, what we see in there is just the 2 light beams overlapping. And the principle, what we use, the workhorse of our whole thing, is interference of light waves. And interference of waves is a thing that you're all familiar with, even if you don't know it. You see it in your everyday lives. And it's kind of, you may have seen it if you're in a sound auditorium or if you're in your home and you're listening to music. If you walk around in different places, when the sound is going, there will be dead spots in your home or wherever you're listening to music. And those dead spots happen because the sound wave that's coming out of the speakers happens to be in phase or out of phase. And so when they're out of phase, maybe between your left hand and right hand speakers, the sound at a particular frequency will seem to go dead. And that's because at the same time that one of the speakers is pushing, the other speaker is pulling. And so when they're doing like this, then you don't get any sound. And to get constructive interference, both of the speakers have to be doing this at the same time. And so that's the basic idea of interference and interferometers. We happen to be using light instead of sound, but the waves are the same kind of thing. So here are some colorful pictures, and I wanted to give you an idea of the kinds of things that we're searching for. So out in space, most of the stuff that we're looking for are sort of the endpoints of stars. Now, if you look at something like our sun is something like 1,000 times heavier than the whole Earth. And it's of course, the heaviest thing in the solar system, and it governs the orbits of all the planets and that kind of thing. And the kinds of objects we're looking for are something like 5 times heavier than the sun or so. And so what happens is a regular star burns its fuel for a while and it shines for millions and millions of years. And finally, when it runs out of fuel, all that's left is whatever atoms are in the star, and that kind of collapses under its own gravity, and it forms these tighter compact objects. And that process of burning and collapse is really energetic. It's a kind of dramatic thing that happens in the universe. And each of those things we can look for. And so starting from, let's say, the bottom right, you see the red thing with the yellow fields around it. And that's what we call a neutron star. It's a star that's just made of subatomic particles and it's been smashed together to sort of form a big atomic nucleus. And then there's also things like supernovae and black holes and that sort of thing. Up till now, the only thing that we found any signals from, even though we have all of these astrophysical objects that we think we could find, so far the only thing we found is the merger of compact objects like neutron stars and black holes. If you look out into the night sky at night, you see the Milky Way galaxy. If you're not in a city, if you get a clear view of the night sky, and you see that there's, lots of stars out there, as many as you can never even count all of them. And our galaxy, the Milky Way, has something like 100 billion stars in it. And half of those stars, maybe 50 billion, are in binary pairs. So they're not alone with planets around them, but there's stars that are orbiting each other all the time. And so of these 50 billion stars, once in a while, they run out of fuel and they collapse into these really dense objects. And then when those dense objects orbit around each other and smash together, that's a energetic enough event that you can measure the space-time fluctuation here on Earth. And so that's roughly the kind of thing we're going for. Now, I said that the signals are really weak. And the reason that the signals are really weak is not because they're weak intrinsically. If you were standing next to one of these things, you're an astronaut in a spacesuit and you got close to these objects, when they do this thing and they merge together, it would really be a painful event. If you're sort of sitting next to them, the stretching of space itself would stretch your body, and you would probably be pulled apart by these kinds of things going on just from the gravity. And so it's incredibly strong where it is, but most of the signals that we find are coming from extremely far away. So, and what do I mean by extremely far away? It's not like across the United States far away or something like that. That's only a few thousand kilometers. It takes, at the speed of light, it takes about 1/100 of a second to go from San Francisco to New York. It takes light about 8 minutes to get to the sun. So the sun is much further away from us than anything on the Earth. That's only 8 light minutes. The galaxy, the Milky Way galaxy, when you look up and see it, that is 100,000 light years across. And so the galaxy is 100,000 light years, so it's very big. And the whole solar system is sort of like tens of light minutes or maybe a few hours or something like that. So the solar system is tiny compared to that. And the objects that we're seeing signals from are more like a few 100 million light years away. So they're something like 1,000 Milky Way galaxies away. And so by the time the signal gets to us, it's just weak because it's traveled so far. But our instrument is sensitive enough so that we've now seen signals from things that are a billion light years away. So because of the way the universe is and expands, when you get a signal from a billion light years away, that signal traveled at the speed of light for a billion years. And so we're really looking back into time to where the universe was only a billion light years, 12.7 billion years old instead of 13.7 billion years. And our ambition is to go deeper. And eventually we want to go back to the point where the universe was only a tenth of a second old or something like that, and really look into the heart of the Big Bang. And this is just to give you a little bit idea about the rainbow. I titled the talk, The Rainbow of Gravitational Waves. And what I mean by that is that there's signals of all different kinds. And we've got signals that are fast, and in the audio band, like I described, they sound like chirps, like a woo kind of signal. But there's signals that are much slower. And just like on the Earth, there's things like hummingbirds that are really high pitched. There's things like bats that make sounds that we can't even hear. They're ultrasonic. But then at the low end, there's things like elephants and whales that communicate at frequencies that we can't hear. And just like you have to have the right kind of ears to hear the right kind of sounds on the Earth, you have to have the right kind of instruments if you want to hear low-pitched or high-pitched gravitational waves. And at the moment, all that we have is the thing on the right. We have detectors on the ground that can hear these signals from space that are pitched right for us. But we have plans to put machines into space to look for signals that maybe oscillate only once a year or once every 10 years or that kind of thing. And those are sort of in the plans. Now, I want to, this just gives you, I'm going back again to the picture of what is an interferometer. So if you look at the object on the left, again, there's this idea of a laser. The laser is split into two. And then it looks about what you've seen before. It's this L-shaped thing, which is called a laser interferometer. But if you look closely now, I've added this extra complication. And so close to the beam splitter, I don't know, can you see my mouse pointer?
Yes.
Okay, so here next to the beam splitter, there's this other mirror. And what we've done there is use a trick. And we've said, well, yeah, it's good for the laser light to travel through space and come back and read us the signal, but wouldn't it be great if we could measure the same thing 100 times and then just add it up? And so what we've done is place this other mirror here. And so the light passes through it, and then it bounces around up and down this tube about 100 times. And then it comes back to our detector. And doing that is really the major trick by which this whole thing works. We're able to add up the signal by 100 times, and we really build up the signal gain in that way. Now, this all seems a little bit abstract, so I want to show you what is actually built. So there's a picture on the left, which says Livingston, and that's kind of in the marshes of central Louisiana. It's about an hour north of New Orleans, and you can see it's in a place covered by pine trees. It's a pine forest that's been cleared out for this purpose, and it's really swampy around. But it's kind of an isolated area. So except for when people come by and chop down the trees for tree farming, it's pretty quiet. There's a question, people often ask this question, you know, if a tree falls in the forest, do you hear it? Yeah, we do. So any tree that gets chopped anywhere within about 5 miles of the LIGO site, it creates a thump, and we see it in our detectors. It's a big problem. So we do our best science at nighttime when no one's chopping trees down. In the summertime, it's tough because the sun is up later and there's tree chopping going on until 8 o'clock at night or so. And on the right-hand side is the same thing, the same object, or the same kind of, it looks the same, but it's in a desolate area. That's Hanford, Washington. It's in the southeast corner of Washington state. And that's where the Hanford Nuclear Reservation is, and where plutonium was enriched before World War II. And still a lot of nuclear work goes on there. but it's very empty and quiet. And so we also like that place. And if you look at these, it just sort of looks like some blocks of stuff, and there's tubes. Let me go back a little bit here. So there's these long tubes of laser beam. And in this picture, you can kind of see there's this white tube that goes off into the distance. And some, in the Louisiana picture also. Those tubes are about 3 meters or so across, about 10 feet across. And they're 4 kilometers long, so about 2.5 miles. And so we've built these things in the middle of nowhere that are these huge L-shaped tubes going off into nowhere. And they're completely empty. All of the air has been pumped out of them. So it's the vacuum of space that we've created in these long tubes. And we had to do that so that the laser light can travel through there without getting disturbed. And I've spent a lot of time at both places. It's a lot of fun to be out in the middle of nowhere and working on these things. But there's a lot of challenges. If you can imagine, if you're sitting in a pine forest in Louisiana at midnight tuning your instrument, the things that you have to deal with are things like hurricanes in the Gulf of Mexico. There's animals that run around. We've got cows going up and down the tubes that you have to account for in your experiment. It's filled with frogs and crickets and all kinds of snakes. And part of being a experimental physicist, instead of the kind that does equations on the chalkboard, is you have to deal with these animals if you want to do your measurements. And so while I was a student, I learned about cow fences and like how do you keep deer from jumping over the tube. That tube, you can maybe see for scale, there's this parking lot over on the side, and these are a bunch of usual cars. So this is an immense instrument. But you often get this thing happening where a deer comes running from one of the sides, charges at the beam tube, and then just leaps completely over it and just goes on. And we worried for a while about whether or not the gravitational pull of the deer was going to disturb our measurements. And the answer is, yeah, it could, but it's got to be a really aggressive deer, and it would have to go head first into the building to make an impact on us. So we're mostly fine. But in the future, we'll have to learn how to measure and subtract the gravitation noise from animals if we want to do better with our instrument. So there you go. That's some biology and physics. And just some other pictures here. There's also instruments in Pisa, Italy. That's where the Leaning Tower of Pisa is, and they, nearby they've got this detector. There's one in Germany, in Hanover, and then one in Japan underneath in a mountain where they hope to do better. And so most of these, if you look at this map, most of our sites are in the US and Europe and Japan. And recently, we've added this new one, or anyway, it's in the works, one in central India. And that one looks, this is a conceptual drawing, but the idea is that it'll look much like the ones we have in the US. And the idea of it is if we have enough of these dotted all over the world, we can triangulate and find out where the sources come from in the sky. So it's a little bit difficult. If you just have one microphone and you hear a sound in it, you don't really know which direction it came from. As humans, we have 2 ears. And so by looking at it's not something you have to do, it just kind of happens in your brain. But when you hear sounds, you can kind of tell which direction it came from if you move your head around and walk around a little bit. And same goes for gravitational waves. The more of these things you have, the better you do. Now you can imagine if you've got 2 ears and your head is really narrow, your 2 ears are almost on top of each other, so you can't tell the difference between which direction it came from. And you don't have an ear on the top of your head, so you can't tell the difference between a sound that came from right in front of you or up above or something like that. And really what you want, if you want to triangulate sounds, is you like to have a head that had ears on the side and ears on the top and bottom and that kind of thing. You could really find out where things come from. That's kind of what we're trying to do. We want the globe to have 4 or 5 of these things so you can really point and figure out where in the sky things come from. And the reason for that is we like to tell the astronomers, the other astronomers, the ones with telescopes, we found something over there and that's exactly where it is. And you should point your telescope there and see what happened. So we've been running now for a few years and we've had about 100 of these things detected. And they're all different kinds. But if you look at these wiggles on the screen, these are the waveforms of the strain. So this is kind of the sound. If you stuck this into your computer and you played it, you'd hear different chirping sounds, and they all have different sounds. But the first one of our favorites, this red one at the top, we found in 2015 in September 14th of 2015, and that one made a sound like boom, and that's it. And it was really quick, and that's why the waveform is so short. But if you look at another one of these, I don't know, pick one of these longer ones here that goes on forever. That's a more dramatic one. That sounds a little bit more like oh, and it's more dramatic. You can listen to the whole thing happen, and it takes a long time. And the amount of time that it takes to radiate and then come together has to do with how heavy it is. So the littler stars take a long time. They just keep on rotating because they don't have a lot of energy to radiate away. But if you have massive black holes, those things almost immediately merge. And so those are short things that are deeper bass kind of sound. So I want to tell you something a little bit about the expansion of the universe. How do we even know that the universe is expanding? You know, this is one of those things you hear about, and like it doesn't feel like the universe is expanding when we're sitting here on the Earth. How do the astronomers know that? Well, what people have done for a long time is they looked around at stars that are near us, meaning like the closest stars to our own sun, and they said, well, we can see the color of these things. They're all yellow, more or less. And now, if that thing is far away from us, we can tell it's far away because it just looks dimmer. So we can just say, okay, well, that's dim, that's far away. When they did that, they noticed that not only are these stars dimmer, but sometimes they're a different color. And that has to do with a thing called blue shifting and red shifting. And just like when you're on the streets and you hear an ambulance come by or a police siren or something like that, you hear the Doppler shift. And as the car comes toward you, it's sort of a high-pitched sound, like beep. And then as it goes away from you, you hear a sort of lower-pitched sound going away. And that's a audio Doppler shift. So things that are coming toward us quicker, we hear them at a higher frequency. And when the things are going away from us, they sound like they're at a lower frequency. And that works as well for light. So if the ambulance was really fast, like close to the speed of light, then as the ambulance came towards you, its flashing lights would look blue. And then as it went away from you, it would look red. And that's how it is with stars. So when we look far enough out into space, you'll see that these things which are bright or dim or whatever, they have different colors. And by looking at the color of the star, you can tell how fast it's moving away from us. And so astronomers have been doing this for about 100 years, and they now have a picture which is pretty irrefutable that the universe is not only expanding, but it looks like it's going to keep expanding forever. It's not settling down; it's just speeding up, and that's a mystery we're trying to solve. But there's a problem. We have problems in our measurements, and we're not really sure about the expansion. So I was watching this movie on a plane, Thor Ragnarok, and in that there's this lightning and thunder thing going on. And so I thought about it, and I said, you know, that's a pretty cool idea. You learn this thing when you're camping as kids, that if you see a lightning strike in the distance and you count 1,000, 2, 1,000, and then you hear the thunder, you can tell how far away the thing was because you see the lightning strike and you know what the speed of sound is. It's about 300 meters a second. And so if you have to count 3 seconds, then that object is about 1 kilometer away, or maybe half a mile or something. And so you know whether or not it's time for you to run or get indoors or not by how long it takes the thunder to hit you. And so we're going to try the same trick. Just like we've got these stars in space that are bright and we can see those things, we want to figure out the expansion of the universe by listening to the sound. So when the black holes merge, there's no light because they're black, they're just dark. And when they merge, there's this vibration, and we sort of hear the sound in gravity. And so we're going to compare this sound and the light and sort of, figure out what the expansion of the universe is in a different kind of way. And let me skip a few here. I was going to, there's more equations here for some reason. I guess I can't get away from equations. Let me go on to a little bit about technology. So I want to just show you a few photos of what these machines actually look like. So the LIGO effort started really in the 80s, and it was designed in the 80s and the 90s. And in the late 90s, we started the first version of it. And then you can see there's me on the left, looking very young. And you can compare that to my age now. That tells you something about the expansion of me rather than the universe. And you can see all of that stuff around. It's springs and steel and welded joints. And that was the height of technology sort of in the mid 90s. And that's what we used. And with that machine, we ran it for about 10 years and we didn't see anything. And that was very disappointing. But then we built a new version of it and we did see something. And there's a picture of me again on the left. You can see I've expanded since that time. And there's my grad school advisor, Ray Weisner. And we're looking at some another interferometer and some prisms. But the technology has really evolved in the last 20 years or so. And that is really what enabled the detection for us. It was really a lot of precision engineering. And this is another similar plot is sort of showing what we found so far. And here, these blue circles are all black holes. And so if you see them, there's these arrows, and there's two blue little arrows, and then they are two little blue circles. And then there's an arrow pointing up, and it goes to a bigger one. And the idea there is that you start with two littler stars, they merge together, and you get a big one. And that seems to be the case. And we've now found things that are, like you can see on there, there's something like 100 times bigger than the mass of the sun. And that was a really a wow time for us to find out that the universe is filled with things that are this big. We've never seen those things before, and it was kind of doubted that those things would exist. If you'd like to know more about black holes, I'm just flashing this thing here for you. It's a great diagram, and I encourage you to look at the YouTube link down there. Google it, and you can find a lot more about black holes. So this is a graphic of the brief history of the universe. I wanted to sort of tell you about what's going on. What do we think our picture is of the universe? So there's a Big Bang all the way on the left-hand side, and I don't have much to say about that. The Big Bang is really a place where we don't have much to say, and really all that scientists can talk about is what happened after the Big Bang. We don't have a way yet to look before it, and we don't even have any ideas. And so the concept is that there was a Big Bang, the universe quickly expanded, and it was really hot. And then over the past 13 billion years or so, the universe has been expanding and cooling down. As the total energy gets diluted, the universe cools down. And when it cools down, it's a little bit like what happens when you freeze water. You freeze water into an ice cube and you see bubbles form and that kind of thing. And you can think about our galaxies and stars and us, everything that you see now is really generated from this Big Bang. And we're sort of what happens when you take a Big Bang and you cool it down. Things congeal and come together through gravity, and they form intelligent life. And we have Zoom sessions and things like that. That's, I guess, what happens. Let me move on a little bit. If you let scientists talk for too long, they just go on. This thing would go on for 3 hours or so. So I want to give you a little flavor for what we've done and what's happening next. So this is a picture of my I wouldn't say ancestors, but my predecessors. So the group at Caltech around the time I was born. Here they are, and it's interesting. There's a collection. Everybody almost on there is a theoretical physicist. They think about things deeply. They do a lot of calculations, and they work chiefly in their minds. And on the left is this guy Briginsky, who was a great Russian physicist who was an expert in measurement, and he used to visit us here in Southern California. And it was really the combination of these minds that think about things in really different ways that launched this whole field. And I'm hoping to capture that kind of magic again. We're trying to build up the same kind of group of people with a bunch of different talents, talented engineers, mathematicians, physicists, chemists, everything out there, whoever has some kind of talent and thinks a little bit differently. And one of the reasons for this is the sort of the ultimate question that we have is what's really going on in black holes? And it's a thing that you hear about, in media and so on, and scientists talk about, but when it comes down to it, we don't really know what's happening right at the black hole surface. We know that it's a sphere and it looks dark and there's a lot of gravity going on, but if you were to get up close to it, what would it really look like? Is it black or is it multicolored like this image on the right? And Stephen Hawking kind of exposed our ignorance about this in the 70s when he was visiting California. And he said, hey, look, if you get close to the black hole, it looks like our laws of physics don't work right. You've got quantum mechanics, which tells you about atoms and light particles and all these things. And then you have Einstein's theory of relativity, which tells you about space, curvature, gravity, and these kinds of things. And when you try to put these two things together, it doesn't make any sense. Somehow gravity doesn't seem to behave like quantum mechanics will tell you, and quantum mechanics doesn't seem to have gravity, and what's going on. And the situation has advanced a lot over the decades, but we still don't have an answer to Hawking's questions from the 1970s. And so that's sort of the quest that we're on here, is to build better and better instruments. And instead of just giving you these wiggles and making these humming noises to you, what I'm hoping is eventually we'll have a system which is like a hi-fi audio system. And if you ever listen to AM radio or transistor radio or vinyl records or cassette tapes, that's a pretty lo-fi thing. You don't really hear what's going on in the instruments. And it's incomparable to a live performance. And so what we want to do is to be able to listen to this smashing of black holes as if you're really there and seeing it in person and getting the most hi-fi audio that we can get. So I'll conclude there. I hope you got a flavor for what this area is and what it's about. And I'm happy to go into as much detail as people want to hear if you have questions. Thank you.
Thank you, Dr. Adhikari. May I and may we call you Rana just for...
Yeah, please do.
All right, thank you. I look forward to seeing hands raised or questions typed in the chat. I've got a couple questions for you, Rana, that can just grease the skids here, allowing other questions to come in. You mentioned that when we first interacted via email that you liked the description of a shaking fist as making gravitational waves, although weak waves that in principle could be detected. The deer that you mentioned that LIGO detects, I take it, is the issue, even as the deer moves, the change of its gravitational pull on the space inside the mirrors might cause a change in what you're reading? Or is it more that the deer's hoofs bang on the ground would physically move the apparatus in a way that beyond gravity?
That's right.
Is the issue?
So at the moment, all that we're getting is the hooves and that kind of thing, because it's just shaking the ground. Okay. But as we've been working better and better, our system uses some of the most advanced vibration isolation out there. So it's almost impossible nowadays for you to, stomp on the ground and have it affect our machine. It's really well isolated from that. And so we're almost at this point now where the main effect is the gravity from the body of the deer affecting the mirror, just pulling it, just like the moon pulls on the tides of pulls on the ocean of the earth.
Wow, that is very cool. I see we have a question from Amir Khan. Amir, do you want, unless I see your hand up and hope you would make yourself audible, I'll go ahead and read the question. Thank you for trusting me, Amir. I have a question on the length of the tubes. Why do they need to be 4 kilometers long? Would shorter tubes not work to detect the signals?
It's a good question. For us, it's almost always the case that longer is better. And the reason for that is that when the space is stretched, you'd like to measure as much of the space as you can. And when the space is bent a little bit, if your light can experience more of that bent space, you do better. And so, yeah, it's a great question, because I think in the future, I'm thinking like hundreds of years from now, I don't think we're going to be going around with giant machines like this, but you'd have some sort of pocket detector that would tell you about gravitational waves just with your smartphone or whatever they have in 500 years. But our technology is not good enough. And so right now, we just have to make the things as big as possible to detect these kinds of things. But if you ask me the same question in 100 years, I would tell you, no way we need 4 kilometers.
Amar adds, so it's not a question of the wavelength then?
Um, in some sense, the wavelength of the gravitational waves is hundreds of kilometers or so, and so if we did get to the point where the gravitational wavelength was short, meaning it was a high frequency signal, then we would do fine with shorter instruments.
Rana, the title of this presentation was Humanity's New Gravitational Sense. So the idea is that maybe someday our ability to perceive, to detect in detail gravitational waves might be conceivably as rich as our ability to detect electromagnetic waves, light, radio waves, and so on. Do you hold out hope in that regard? For instance, that we've learned a lot about the cosmos through the spectra we see in the visible spectrum of light, spectra from stars, perhaps even someday from planetary atmospheres. Is there any hope of getting that kind of information encoded in gravitational waves?
Yeah, absolutely. I would say there's an electronics class I used to teach here. And on the Caltech campus, we have bats sometimes, which screech at frequencies of tens of kilohertz. You can't hear it. But for this electronics project, we made a system that records this high frequency noise and then downshifts it to where you can hear the bats yourself. And the idea is, let's take all these different frequencies we can't hear, and we'll compress it into the human audio band. So you would be able to hear elephant low frequency rumbles in the audio band and high frequency stuff. And you hear it with your own ears. You don't need anybody to interpret it for you. And when you look out into the sky, optical radiation is a small slice of the pie. There's gamma rays and radio waves and those things. And you see those things in the news when you see images from the James Webb Telescope or something, or the Event Horizon Telescope, which shows black holes. Those are all things that are not in the optical. The James Webb doesn't see things like we do. It sees infrared, but we turn it into visible images so that we can interpret it. And I think, we already know there's animals that navigate using magnetic perception, birds and so on. And I'm hoping for a day where we have enough kind of wearable technology that human beings can hear wider audio band signals. We can have eyes that see into the ultraviolet and the infrared, like some animals do, and eventually have clothes that will detect gravitational waves, and you can just feel it. And you don't need to have scientists come and tell you about what's happening, but you just be out there and sense nature in that kind of way.
It won't be a 3 kilometer outfit. It'll be able to wear it.
In 1,000 years, this is all going to be possible.
Oh man. Okay, since this is a Wonderfest presentation, let me stretch this idea, this wonderful notion of perceiving gravitational waves that well. When we learned how to detect electromagnetic waves, quite soon people began to wonder whether we would get electromagnetic signals from other civilizations. Do some physicists, perhaps you, some astronomers, say that someday we'll detect gravitational waves from, initially, at least if we're able to do this, from very powerful civilizations, those civilizations that can perhaps play with galaxies, or at least play with black holes, that kind of thing. Is that just too far-fetched, or do you imagine that we'll be looking for SETI, search for extraterrestrial intelligence through gravity waves?
It could be happening already. I would say, for example, what's a good example? Like giraffes or hippos or something like that. They have no knowledge about cell phones, so they don't know that we're communicating on this other network. And to them, it just looks like we have plastic things up against our head for some reason. And it may be that there's advanced civilizations who just don't bother to use electromagnetism because it's primitive. And it might be that the dominant form of communication in the galaxy is through gravity or something like this. And the advantage of that is, when you're trying to communicate with a cell phone, if you go in a basement or you're in an elevator, sometimes you don't get good reception. And that's because things like rocks and metal can block radio waves that we use for the gravitational waves. That's what we use for cell phones. But gravity isn't blocked by anything. So if you use gravity to communicate, you can communicate straight through the galaxy, and it doesn't matter if there's stars in the way or anything. At the moment, we don't know how to do this ourselves. We don't know how to generate enough gravitational energy. Me doing this with my fist is such a weak signal. We don't have any instruments to pick it up. But in the future, if you imagine the whole planet got together to try to do something like this, we would probably be able to make signals that are big enough that you could measure it in the next solar system if we really wanted to do it. And it's sort of at the limits of of human technology right now, but it'd be like $1 trillion project, and so we wouldn't do it. But for an advanced civilization, sure. I mean, people who can harness the power of a star, they could easily make enough energy to communicate across the galaxy.
Very cool. Thank you, Rana. Gorgo Mund asks, when you detect a gravitational wave, how do you know what caused it? Does this require observational astronomy?
Yeah, this is a great question. I mean, this was the main worry of people in this field for so long, that you have this instrument and most of the time you're not seeing anything. It's just a hiss, like if you're listening to a microphone that's in a sealed room or something like that. And just because you got a little signal, like a bump in the night, doesn't mean that it was a real astrophysical thing. So we have a few tricks. We have these multiple detectors to make sure that it's picked up in 2 different places. And then we have a bunch of environmental sensors to tell us about earthquakes and traffic. We have magnetic sensors to rule out lightning and thunder and those kinds of things. So we detect everything that we possibly could to rule out any kind of local thing. For the binary black holes that we detect, there's no other kind of astronomy that picks it up. The black holes merge and we're the only ones who get it. But in 2017, in August, we witnessed the merger of 2 neutron stars. And that's not black holes, so it's not dark. It's actually a bunch of nuclear matter smashing together. And that produced a flash in every electromagnetic wave, from gamma rays to X-rays and ultraviolet, the whole rainbow of electromagnetic waves. And so I don't think this ever happened before, but it was something like 1/3 of all the astronomers on the planet Earth observed that event, because it was the most spectacular thing we've ever seen. And not only was it a great signal for us, but when people studied the spectrum, they looked at the colors of this thing in the different wavelengths. They saw that when neutron stars get smashed together, it finally explained this mystery of where do all the heavy elements come from. You know, if you look at the periodic table of elements, down at the bottom, there's all these strange things like praseodymium and neodymium and whatever, all the big things down there. And we didn't know what in the universe makes that stuff. But now we think it's pretty clear that when neutron stars smash together, there's enough energy to make big atoms. And so when you look on the Earth and you see things like platinum and gold, lead, uranium, all these things, that stuff most likely came from the merging of neutron stars billions of years before the Earth was formed. And that dust, those fragments, the ashes of that kind of explosion congealed into the planet Earth. And that's what we've got. The Earth's crust is just filled with the remnants of mergers of neutron stars.
That same questioner, Gorga, asks, how do you know it's 2 black holes, or say 2 neutron stars, when you get a signal?
Great question. So let's see, let me try to scroll back a little bit through my pictures, and I'll show you. It has to do with the same way that when you listen to the chirp of a bird, how do you know what bird it was? And you know it because you recognize the sound, and you have in your mind, you say, okay, well, that's a chicken, or that's a magpie, or that's a parrot, or something like that. They have a distinctive frequency and timing and it's a character of it. And for us, it's like that too. Any difference, if you have little black holes or big black holes or neutron stars or what are the different things, depending on what are they doing and what are they made of and how are they spinning around, they produce a distinctively different wiggle in our detectors. So we look at these wiggles and we do the equivalent of what your ear does, is we play it through something that's a lot like a pattern recognition device in the mind. And we play that sound and we see which thing does it match up with. And then we have already pre-calculated all of these different kinds of signals. We look to see, okay, what does that mean? How big are they? And where is it in the sky? And how long ago did it happen? And it's the amazing thing about this experiment for me is that this is a theory that Einstein came up with over 100 years ago. And we're now finding these signals. And, to better than 0.1%, these signals that we detect match exactly what he would have predicted. If he had had computers that could have done the calculation.
Yeah. Stephen Ramirez asks, is mass and the interaction of masses the only cause of gravitational waves?
Oh, I love these questions. These are the. I wish my students would ask me these kinds of questions.
These are the wondernauts.
These are great questions. Mostly that's what people think about, mass and the interaction of mass. But I think that's not right. I think there's more to the world than just masses. And to give you a flavor for it, I work by analogies a lot because I'm not a theoretical physicist, so I have to kind of dumb it down for myself. And the way I like to think about the universe is space is this big fluid, and we're all swimming through it all the time. But it's like fish in the ocean. They don't really think about what's the nature of water because that's their universe. And we don't think about what's the nature of space-time because it's empty space to us. But it's got some features. Obviously, gravity is hidden here and that kind of thing. And in water, you can get these events that happen where a bubble just forms that comes out of a fish's mouth, or a piece of the water will freeze into something or something. And so space itself can have these kinds of things going on. And I think there's probably stuff going on out there like that, where space-time itself crackles and pops and turns and changes character. And those kinds of events can make gravitational waves. And so anything that has energy will do it. And that comes from Einstein's E equals mc squared. What that really means is how much E do you need to be the same as some amount of m, which is the mass. And E is the energy, m is the mass, and c squared is just the proportionality there. But if you have as much E as a black hole mass times c squared, you can do the same. And it doesn't really matter whether it's mass or energy.
Michael Snodgrass asks, is the tidal effect, let's say from the moon, noticeable over only 4 kilometers on the current LIGO?
Well, no. So we detect the moon all the time because there's the earth tides. So the fact that we have high and low tides is a detection. But it's funny, actually. The first time, so probably in the late 90s, late 90s, early 2000s, I was operating one initial part of LIGO, and I noticed this thing that the signal kept drifting, and it took hours and hours to drift, and I couldn't figure out what was going on. And then later that night, after a long night of debugging, we were driving home, and I saw where the moon was in the sky, and the signal that I was trying to debug all the time was just the moon. And because the moon was traveling around, it was sort of slowly stretching our device. So the first thing that we detected with LIGO was the moon. And I could have just gone outside and looked out a window, but I didn't know. I mean, I didn't have a window in that office, so I couldn't tell what was going on. But you don't need it. You can. A lot of people detect the tides from the moon and the sun using seismologists and geophysicists do that using their instruments also.
Rana, I promised you, and I promised the Wondernauts here that your presentation would end after an hour. So I feel a certain duty here to draw this to an end. But after a few other words here, I want you to know how much we appreciate this. And I want to thank everybody for being here tonight. Remember that our next online event happens on August 17th, 1 week from tonight, in collaboration with the Commonwealth Club. It's Understanding the Milky Way with astrophysicist and folklorist, Dr. Moya McTeer. Wonderfest.org is the place to go to learn about that. I end tonight by offering 3 big thank yous. First, to you, the Wondernaut audience. Second, to our Wonderfest supporters and patrons. You too can support Wonderfest if you'd like. And most of all, thank you to our speaker, our gravity explorer and laser lover, Dr. Rana Adhikari.